Thanks for joining us, guys, today. I'm TK, and this is Alex, and we're here to talk about some of the growing pains at Pandora. We're two engineering dudes. We were trying to fix the build with our team of about 5 or 6 people. So we'll take it through the journey. But before we dive in, I want to give you a high-level overview of some of the growing pains and some ballpark numbers so you can understand the problems we were up against. So back in 2013, we had about 50 developers, and we had about 30 modules in a big monolithic code line. The code line was in Perforce, and there was a mix of about 85% Java code. The rest of it was C and some Python modules. So over the next couple of years, we had an explosion of new engineers. We just about quadrupled the number of engineers, and we added just about doubled the number of modules. So when we had about 50 people, it was all good. We were all working on the same code base, but we were working in different modules. But with the additional people and additional teams, we started to work and converge on some of the shared code, and it was a big problem. As well as the build, in 2013 was taking about 20 minutes, 25. And by the beginning of 2016, the build was taking about an hour. And if you look at the test times in the upper right-hand corner, what used to take about 35 minutes for running all the tests, by 2016 was taking about 3.5 hours. So there was a lot of context switching, and obviously developers were not very happy about this. So we knew we had to change a lot of things in how we build and distribute modules. So let me walk you through the base setup in this legacy code line and how we build stuff. So at the very top we had make. Like I said, most of the code was Java, but we also had Apache and some Apache modules in the same code line. That stuff was almost never changing, but Make was orchestrating the build as well as building the C dependencies. And whenever Make was trying to build a Java module, it would delegate to Ant. So Ant would compile the Java code and do the packaging. And for the Python modules, we had mostly setup tools. A lot of these modules were statistics, machine learning, stuff, and mostly using setup tools, but some of them were slightly different. So to glue all of this monstrosity of different tools and technologies, we had a bunch of bash code like sprinkled all over the place. So the main takeaway from the first slide is we had a huge explosion of new engineers, an explosion in complexity, and number of modules in the code line, and I think the biggest problem was build times and just general productivity decline. So the huge combinations of different tools and technologies was also introducing a lot of fragility. So whenever something failed in the build, we had to spend a lot of time investigating the issue and getting to the bottom of it. It could have been one of those 5 or 6 tools we were using, so it was definitely tedious. We were also mixing a lot of languages, so mostly Java, but the C code in the form of Apache and some Apache modules was almost never changing. And yet it was in the same code line. It was convenient. We could deploy everything in one go, but it was a pain when you had to do a clean build and wait for all that compilation to happen. The same goes for Python. And of course, all of the front-end code was backed by CSS, JavaScript, and other static assets, which were being shuffled by the build all over the place. So we started this journey back in 2015. And one of the main points we want to make today is that you can make significant changes and attack these problems with very limited resources. So our team does a lot more than just deal with the build. So we couldn't allocate the whole team to build issues and making those changes. So we had to be very strategic about this. So we started with about 2 engineers working on exploring different tools and technologies and making small changes and tweaks. So right off the top of my head, if I have to think about a Java build tool, Maven immediately comes to mind. But Maven had some story, some backstory at Pandora. We attempted to migrate to Maven back in 2012 with very limited success. So I think the biggest problem back then was how customized our build was and how hard fitting this Maven's mantra of convention over configuration on top of this monstrous build. So, of course, since we attempted Maven, there was not a lot of buy-in, and we didn't have a lot of Maven experts at Pandora, especially among the most senior engineers. So we knew that Maven is a good option, but probably not the best tool for us. We also explored other tools like Buck and Bazel. So because most of our code is Java, we wanted to choose something that's Java first and is very popular in the Java community. We wanted to avoid having to educate people joining Pandora about these new tools. And we wanted to get all of the new engineers who already understood Maven and Gradle be productive on the first day, if possible. And finally, we had Gradle. So Gradle was growing in popularity. There was good documentation, a lot of resources out there. So we thought that Maven and Maven's ecosystem was pretty stable, and Gradle was piggybacking on top of that. So for us, and being mainly a Java shop, it was mostly a natural choice. So we went with Gradle, and we also adopted Nexus and started publishing version artifacts. So up until then, we were mostly keeping all of the dependencies in this code line, and it was like really tedious. We were basically taking the latest version of everything every time. So whenever you had to do an update, it was a lot of work. And finally, we started adopting SonarQube for keeping quality metrics. And Alex will talk a little bit about SonarQube. All right, so most of the work we did over 2016. The first steps we did was taking a look at the high-level modules, the stuff that was living at the top, the stuff that everyone was converging on. So we took those shared dependencies and we refactored them out and put them in Git with a separate build. And we started running the tests in those smaller builds. So with that, we started publishing version dependencies, and that mainly decoupled a lot of the teams converging on this shared code and allowed them to work independently without having to take the latest code at the same time. I just want to mention one of the big steps we did, which is implementing the Pandora parent plugin for Gradle as one of the big wins. And I have a slide dedicated to the parent plugin. I want to give you more details, but I want to mention that as one of the big steps. And with the parent plugin, we also developed some other plugins that helped fold a lot of the stuff that made sense to be in the build. Like some of the modules were needing Kafka schemas, so whenever we needed that, we were delegating to this custom Kafka plugin that we implemented. And the plugin was publishing the schemas to our Kafka registries. And we also attacked the duplication of config files, all of the boilerplate that was sprinkled all over the config files with a templating plugin, which collapsed all of this complexity and allowed us to have a lot of shared configs. And finally, Maven back in 2012 was mostly a failure because we didn't have enough resources and documentation to help people out with issues. So this time we wanted to not repeat this problem, and we started with education first. So we created a dedicated channel where people can go and ask questions. And we had a couple of guys dedicated to manning that, as well as all of the people that were getting up to speed with Gradle and sharing a lot of resources and knowledge in the channel. So we accumulated a good knowledge base of common questions and common problems in Slack. And we started moving a lot of this stuff to separate wiki pages that people could reference and share. So with that, we also scheduled a lot of hands-on workshops at Pandora, mainly to make people experience Gradle hands-on without even using any of the new Gradle modules we started creating. So the hands-on experience, I think, helped people get really comfortable and increased adoption. So I promised a few more details about the parent plugin. So the plugin came out of the need to eliminate a lot of the boilerplate from all of the new build files and all of the new repos that we were creating from the shared code. So that was the immediate need. But we realized that it was a big win for baking some best practices, injecting additional metadata, just getting consistency across all of the builds with a single plugin. So if we needed to yank, for example, a bad version, we can just put all of that in the parent plugin and apply across all of the builds at the same time. Another common problem that we experienced right from the beginning was with this increase of shared dependencies. A lot of the teams working on the same dependency were stepping on each other's toes when publishing snapshot artifacts. So if you have team A working on a feature branch A, making changes and publishing a snapshot, and team B working on the same repo but publishing a snapshot from another feature branch, they were constantly overriding themselves. So we solved this problem in the parent plugin as well by tagging the snapshot versions with the name of the feature branch that the code was coming out of. I also want to mention some of the common plugins that we apply pretty much across all of our modules. So, for example, the release plugin has been a great help for enforcing some of the best practices, as well as making sure that there are no local changes when you publish a dependency or a snapshot. And also, last but not least, I want to mention that the parent plugin was a good way to increase adoption of Gradle as well. We outsourced, and we had another team helping with a lot of these efforts. So this helped us generate additional knowledge in other teams who were then able to help us basically support other teams with Gradle. So now I'm going to hand it over to Alex, and Alex will talk us through some of the more advanced optimizations we did with Gradle.
Hey, nice to meet you. Nice to see you all here. My name's Alex. And you know, I spent almost all my working career working on different automation and optimization, being a DevOps engineer. And I joined Pandora recently when strategy was almost finished. And we had a strategy architecture for everything, but it was time to finally implement this. We started with moving C and Python code out to Git, and it helped a lot. We cut approximately 25% of build time. And it seems to be a success, but you know, it was definitely not enough for us. And approximately Right, so approximately in fall 2016, I started working on parallel Gradle build for this huge monolithic code base. So we moved out some of it, but there still was a lot of sources. And at that time I was joking that it might be a great Christmas present for engineering department. It was actually not the joke, it was true because I finished it and finally committed the latest changes. Approximately December 19 as regional Jenkinses to build using Gradle versus old Make Lassans. And it was a huge success right from the beginning because we were able to cut the build time from approximately like 45 minutes to 12 on developers' laptops using macros, and we're also utilizing Vagrant to kind of test the changes in environments which are very close to production, which are using Linux. And inside Vagrant VMs, it was around 18 minutes. And it seems to be a great result. But you know, at that time, for me, it became kind of a sport. It was a sport competition to cut as much as I can. So I started checking different incubating features, playing with settings, deep settings, creating custom scripts to optimize it even more. And a part of parallel builds, we noticed that because the code base is still huge, it has a lot of modules, we can save some time by switching always on configuration on demand is one of the incubating features. It helped a little bit, saved like, I don't know, 35% of time. And the last step, one of the last steps was enabling the local build cache. Because again, usually developers work on 1, 2 modules, 3, and out of, let's say, 50, it means that every time if you're running clean build, you will have to recompile all the sources to all the stuff. So in this case, if you're using local build cache, it will save your time. Plus, we did additional optimizations like number of Gradle workers, because we don't have default settings. And in the end, I would say that we also suggested our developers to use, okay, like you sync your code, and the first time you need to build, but next time you can switch off checking dependencies versus the Nexus, I mean, switching offline mode on, which also finally allowed us to cut the build times on macOS to 6 minutes. That's why we actually call this presentation our journey to 10 times faster builds, because at that time we had 6 minutes versus 60 minutes before. And even this was not the end. When you move a lot of code outside, at some point you start to experience this problem that you have to follow standard workflow. Like you have a small repo in Git, you're cloning the repo, you're creating feature branch, you're making changes, creating PR, merging, publishing, releasing. Now you need to get to the next repo, which differs on first, and change the version. Make the same changes over and over and over, which actually slows down you really seriously. And approximately at the same time, we started contacting Gradle team. And they proposed to try using composite builds. Unfortunately, due to nature limitations of composite builds, for example, it supports only main artifacts, while we have a lot of different custom packaging, classified artifacts, and so on. Plus, some additional limitations, we were not able to apply composite builds at organizational scale, but we do have a real success for some of the team utilizing composite builds, because we created separate repos, which are actually kind of core of the composite builds. We even tried to combine it with Git submodules. And for some of the teams, it's really successful. It was really successful, because now they're able to work with the virtually huge project, which is actually contains a set of little Git repos inside of it. And about the source code quality, you know, we installed the SonarQube and started massively publishing information about every release to SonarQube, and we accumulated a lot of information, but we noticed that the developers usually don't have time to check how the changes affect the source code quality. It's just it's not a matter of being bad or whatever, it's mostly a matter of time. You need to provide a convenient way. And for us, the convenient way was a simple integration. So Jenkins pulls code out of Git, it builds it using Gradle, it publishes information to SonarQube and pushes artifacts to Nexus, while Bitbucket on the other side has a really nice plugin which is able to show a small widget on the PR page, which shows how your changes affected the source code quality. It just compares the snapshot of your feature branch in SonarQube versus the main line. And it was like magic. We immediately saw that developers started to add 1, 2 more commits to their PRs with fixes to SonarQube errors. It was the real magic. And the last, probably one of the most interesting steps, was dealing with the tests. We had probably from 25 to 30,000 unit and integration tests. And running it's at some level of parallelization causes developers to wait for 3 hours for the result. I mean, you can imagine that at this point you can build everything within 6 minutes, but you still have to wait 3 hours until you're actually sure that everything is in place and working. And yeah, you can throw a lot of resources, people resources, hardware resources, set up a huge cluster for it. But we thought that we should try to optimize, like go intensive way versus extensive. The first attempt was just to run unit tests in a small cluster of entry-level servers in batches in parallel. And it got some results, plus additional hardware optimizations like switching off database synchronous writes and stuff like this. But anyway, anytime developers change unit test, remove, add, change the logic, your balance switches. And again, one node might finish in 5 minutes, the second node will have to work for 1 hour to finish unit tests. So at that time, our team came up with the idea, what if we can have a backend and develop a Gradle plugin which will be able to pull information out of this backend before build, to rebalance the test between cluster nodes. And in the end, publish this information back. So we're keeping history how balance of batches of tests across nodes affects the performance. So next time, we're able to fetch this information and try to rebalance. There was a few funny, interesting issues. Like, we had one test, approximately 1600 code lines, which took by itself 15 minutes. And the system was struggling to rebalance it, trying different configuration, but still failing. Yeah, the simple solution for it is just split this into like 4 or 5 pieces. And after a few iterations, the system self-balances itself to approximately 8 minutes. So now imagine the difference we've made. Let's just try to summarize. So build time, we were able to cut from 60 minutes to 6, and task time using just 8 entry-level servers from 3 hours to 8 minutes. If we will try to calculate return of investment, it would be something like we spend approximately 1 man-year to finalize all these tasks. And it's not just us, we saved approximately 1 hour per developer per day. Because when you're making changes and you need to verify, and you need to wait for 1 hour to get those results, it was just a nightmare. Right now, you can get a results within under 15 minutes. Again, less context switching, modular code base, predictable releases, everything attached. And in the end, we realized that we have a huge knowledge about our Gradle build and ways to tune it, ways to optimize the workflow. But developers, unfortunately, they don't know about it. So I hosted a set of meetings for everybody, for everybody in the engineering organization, to explain not just about our build, but in general, how you can optimize and work with Gradle. How you can get the most out of Gradle. It was the basic training. And there is a plan, and there is a wiki page, a plan, a presentation for advanced training. And I'm going to share the knowledge how to actually hook up with the different events inside Gradle lifecycle, how to change the lifecycle, how to create super custom init scripts, stuff like this, resolve problems with composite builds. It's all planned, it's ready. We're going to host it probably next month. And yeah, we can live with this success and like see it and be happy, but it's not about us. We're looking to the future. And we just try to calculate what other problems we have. And realize that, imagine that because of the huge organization right now and changes in Pandora, like introducing premium and so on, we need a lot of new applications to be deployed, small projects. And imagine if you have, let's say, 200 lines of business logic, and you would like not just create a demo on your laptop, but you want to share this with others. You need to request hardware, you need to ask CSAT team to install needed software on this. And it might take not just hours or days, it might take weeks. I mean, imagine how much time do you need to approve the buy order, set up hardware in a data center, stuff like this. We realized that the developers are not happy with this. So the next step, looking to the future. Yeah, probably Bob the Builder for this tool was a pretty common name, I think. But still, the idea around it was to get software from developer to production in minutes versus weeks. So this tool, from the beginning, is supposed to be language agnostic. It relies on so-called templates. Inside template, and templates are different. We have a Node.js template, we have Python Django template, we have different Java templates with support of databases, Kafka, Redis, Memcached, stuff like this. And each template has a lot of placeholders. So developer can log in to this system, select the template, then just fill in the gaps. System will create a Git repo, a Bitbucket, set up permissions, set up owners. Each template, except the code, also contains Jenkins pipelines definitions. So it will automatically, because we do have in Jenkins, we do have a DSL. DSL will automatically pick up those pipelines and automatically create jobs. We do have a Docker file, Docker definition to build a container. We have a Nomad definition. Nomad is a tool which allows you to deploy those containers actually to Docker cluster. But it's not the end. It also uses console for auto-discovery. I mean, you don't need to ask NetOps anymore, please create a VIP or stuff like this for me. It can be auto-discovered through console. Plus, console key pairs allows you to get the key and finally fetch the secrets from Vault. Probably now the Vault is just kind of a shared system for storing secrets. And on top of it, we have Fabio. Fabio is a software load balancer. So if you need not just one node, but let's say you need 8 nodes to be able to do rolling deployments, you can just utilize Fabio to automatically load balance. And this was all developed within approximately a month, and we already started using it. Unfortunately, the only one piece which is still missing is integration with Fabio. We're right now working on it. That's why it's to the future. But mostly this system is used. On the other hand, we're still exploring the flexibility of Gradle. And we're going to we want to expand our usage of build cache, because right now we already have a shared instance of build cache, and we're slowly moving towards applying this settings to all the builds across the company. On the other side, we're trying right now build Gradle Enterprise, mostly to identify bottlenecks and help developers, because you know the situation when developers comes to you and says, oh, my build is failing. And you're like, can you provide me more information so I can help you? And we noticed that Gradle Enterprise is excellent at this, because developers just publish the scan, and you have everything you need to help them. Plus, right now we have ideas of open sourcing some of our plugins. We just need to split the Pandora parent plugin with its configuration, because right now it's baked into, and probably we can outsource it. Open source it, sorry. And on the other side is really interesting examples are TLB test load balancer plugin with the plugin code itself and backend code. I think it also would be a great idea to open source it. And in the end, the plan for the rest of the year, probably for the next year, is to align our builds with our Android team, because mostly what I just explained was about backend builds. We still have a lot of things to do on the Android side, because they do have their own infrastructure, builds, and even engineers to do this. So it's kind of the plan to merge everything together into a single organization. But overall, guys, I would like to say that I think this is a great success, but mostly our presentation was about that huge enterprise companies are usually scared of changes. I faced it because I worked for many huge companies. And managers think that they will have to spend a lot of effort, involve a lot of people, hardware resources to do changes like this. But I think that actually it's about a small team of talented people dedicated to success who could produce ideas and implement them. And actually, I would say that I'm proud to be a member of such a team at Pandora. I would like to thank you, my team, and thank you for listening. And now it's time for your questions.
Yes?
So you mentioned earlier reducing the modules and break them down to smaller pieces.
Mm-hmm.
Is there some kind of tooling you would recommend or some kind of practice?
So a lot of the code we were sharing was pretty much intertwined and was used in a few but key modules. We used Git P4. So like I said, the monolithic code base was in Perforce. So to preserve all the history, all of the commits, we were using Git P4. And then the rest of the stuff, like one of the most important pieces, I think, was the parent plugin. So instead of, especially if you have a highly customized build, instead of replicating a lot of the build steps across many modules, you can fold a lot of this complexity into one plugin that's applied everywhere.
Yeah, actually, because in the end, like standard build, if you don't need anything custom, standard build is like 5 lines.
Mm-hmm.
So you move the code, put the build Gradle file, which contains 5 lines, and that's it. You have a project which is built by Gradle, covered by code, source code quality tools, publish it to Nexus, release it, everything is in place.
Yes?
I'd be interested in like more in your thoughts. So it sounds like you started out with like one code repository that just happened to be Perforce, and then you switched to like a bunch of multiple Git repositories. I've also seen where people go the other way, because having all of the different dependencies is like hard to manage. And whereas if you just have one repository, then you have like a continuous integrated thing. There's a lot of other things.
Yeah.
What were your thoughts on that when you decided to go with the like multiple repositories versus like one?
So for us, we were experiencing a lot of growing pains, and like a lot of the teams were converging on the same modules. So we really needed to have a system for versioning. It's really a choice. I mean, you have some trade-offs between the two models. Like one of the choices we made was around some of the static content. I mean, obviously, when you have a lot of binary files in Git, it inflates the repos significantly. So I can see organizations going both ways, depending on the needs and how they work. For us, breaking stuff down works better and allows us to decouple a lot of the teams. Like most of this code is siloed. Just the top level dependencies were causing a lot of issues, and that's what we took out. We still have a lot of the monolithic build being used by a lot of teams, but the shared code is out.
Yeah, plus there is additional moment that you probably need to measure the actual utilization, not utilization, but kind of number of changes, because we realized that a lot of code we're moving out is rarely changed. But it allows, but with the old code base, when you want to start up a new project, you have to put everything into the same place, because you have to depend on core APIs. But if we move out the core APIs, we do not frequently change it, actually. We can unblock other teams to create their own applications based on any technologies they want. Like if they want to have a Spring Boot application using custom container, go on. Otherwise, you will have to plug it into existing infrastructure in the old monolithic huge code base.
Yes?
The time that you said that you reduced it down from 60 minutes to 6 minutes, right?
Uh-huh.
But does that take into account this monolith versus split repos? Or because now you have all the smaller repos instead of one big repo, right? So the big repo obviously is going to reduce automatically.
So yeah, some of the improvements were because we moved some of the code out, but that said, the code that we moved out probably accounts for about not more than 10%, the Java code. We also had the C code that I mentioned, so that was not built every time, but whenever you needed to do a clean build, or whenever we had something breaking and not accounting, like flagging a module as changed without the module actually being changed, that was increasing the build time significantly. So yeah, it does. Some of the improvements are due to moving code out, but the majority of the stuff was all the tweaks we did with Gradle and parallelizing a lot of stuff.
Excuse me, I don't have exact numbers, but I can approximately try to estimate. Without the code in Perforce, I mean, by moving code to Perforce, we cut to approximately, the best number was 35 minutes with the old build. And in the end, with help of Gradle, all the optimizations we did due to flexibility and the cool features of Gradle, it's from approximately from 35 minutes to 6 minutes.
Yeah, that's on a clean build, including compiling the C code. Yes?
I have a question about that parent plugin you talked about. Like, how
Yeah.
do you manage changes to the parent plugin? Like, do you make your developers pick up the latest version always, or like how, like, you need to choose something? How do you tell them to make sure that new policy is in place?
Yeah, so the question is, how do we manage upgrades of this parent Pandora plugin for Gradle? We have scripts that apply the new versions across all of the repos.
Yeah, so the point is the easiest way was just to depend on wildcarded version.
Mm-hmm.
So anytime we release the new plugin, it's automatically applied to all builds across the whole company.
And if we bump the major version, then we would go and rip through all the repos and update that. Yes?
You mentioned you had a solution for tagging the releases coming from different branches.
Mm-hmm.
So can you talk a little more about that?
Yeah, sure. So the point is that Pandora parent plugin also includes grgit plugin. So we are able to identify the branches and information about the source of this build on the fly while starting the build. So Pandora plugin so far acquires the repository URL, branch, commit hash, and stuff like this. And on the fly, it just changes the version. It's pretty close like certain guys do. But instead of adding a timestamp, we're adding the feature branch into the version. So without changing the build file itself, Pandora plugin applies the change to the version and publishes this to Nexus. So build file becomes intact, it's still intact, while in Nexus, the snapshot has a version which embeds the feature branch name.
And we only do this for non-master branches, and yeah, only feature branches and only for snapshots.
It's a version suffix.
Yeah, pretty much. Yeah.
How do you ensure that another task branch with a higher version doesn't get fetched instead, or like a higher master version doesn't come in when you're expecting a task branch? Does that question make sense?
Yeah, so the question is, how do we make sure that if there's a higher version in master, it doesn't disrupt the tag versions that we published? Okay, yeah, so this basically allows developers to check out the latest version, and if you bump the version, then it becomes a problem. But that said, it's not very common for a few teams to be working on the same stuff as across releases for these dependencies. So it solves the problem when you work on the same version number, but when the version gets bumped, then it's still an issue.
I don't quite recall when you went through the slides. I think one of the slides I saw, the test time also was quite high, right?
Yeah.
For either unit test or integration test. How did the 6 minutes include testing as well, or it's,
And the 6 minutes is just for build, and the test times from 3 hours to 8 minutes. So the whole build, the whole complete kind of building the code from scratch, like it fetches, it deletes the workspace, it fetches the code, the source code that builds it completely, again, utilizing build cache. And in the end, there is a different build, which utilizes our TLB plugin, test load balancer, which splits the tests into batches and runs them on the small cluster.
I see. So that's a separate time additional?
Yeah, so yeah, we have separate jobs. So one job is building this monolith, and the other job is running all the tests inside. So we don't have test breakages in the monolith fail the build, but we keep track of the failures in a separate place. All right, any last questions? All right, thank you guys.
Thanks a lot.